Hello and welcome to my first vlog about a pet project of mine, which is generating book covers through GANs. This is supposed to be my tribute to books, as well as my personal study on generative adversarial networks. We'll begin first with some motivations and discussion on what is a GAN. And then we'll be going through the data that we do have. Then we go to DCGANs, semi-supervised GANs, and an ongoing work of mine. Now, these past months, I've been blitzing through a lot of books, particularly fiction. There's some odd business and popular science books here mixed in. Right? When I look at them through my mini library and ebook collection, I see these wonderful book covers that are no doubt a labor of love for or by their designers. Now, being a machine learning person, I thought that maybe an AI system can learn to recreate these book covers and learn something new in the process. The technology that we're going to explore is the same vein as those deepfakes, those artificial faces that you see flying in the web. As you will see, it's very difficult to create a convincing artificial book cover, let alone a believable face. But it is possible and very fun. The journey will be worth it. Let's begin. Our subject of learning here is generative adversarial networks. Now let's parse this name. Let's begin first with networks. Networks here mean neural networks, a machine learning model which has seen tremendous success in the field, especially with the use of really large networks called deep learning. These networks are actually simplified simulations of the human brain, which are good for classification tasks. Classification is recognizing if a face is smiling or not. Those technologies are found in some really high-end cell phones, or even some mid-end cell phones nowadays. Mind you that training these networks can take thousands to millions of images with days, right? And require high-end GPUs. And at the very end, we can only still replicate a small part of the human brain visual system, right? But it's still useful, right? For example, an image here, Sarah, presumably, is processed by these layers in the network, which capture progressively more complex features until at the very end, it can say, this is Sarah. Now, classification is one thing, but what if we want to do the reverse? Like generating a smiling face, right? Hence, we go to the generative part of our GANs. Our smiling face networks really can't do this since it's a type of discriminative network. It's only been trained to distinguish smiling from non-smiling faces, right? So a team from the University of Montreal, Professor Goodfellow and his team, has created ways to make networks generate samples of images from the domain it was trained on. Turns out there's a lot of ways to make networks generate samples, but an efficient way is through a game-like framework. In this game, two networks compete in an adversarial fashion. The first network, the generator, outputs an artificial image. The second network then guesses if that image is real or not. Now, it has also been trained on real images, so it can distinguish. Now, its output is a probability if it's real or fake, and this will be used by the generator to tweak its internal parameters for the next step, to fool, of course, the discriminator. Convergence through this mini-max game has been theoretically proven, but empirically speaking, it's very hard to keep the training stable. This framework can do more than generate faces. It can be used to alter faces to however attribute we do like. So for example, the folks at NVIDIA did StyleGAN, which can combine these different faces, right? These coarse style faces, middle style faces, and fine style faces into a plausible looking face, right? If you ever want to Photoshop yourself to be a blonde or redhead and have sparkling white teeth, then GANs can make your dream come true. We then go over to the Goodreads book covers data and our implementations for our GANs. For this process, we use the Goodreads book covers dataset, which can be found in Kaggle. It's a collection of 54,000 books scraped from Goodreads, which contains book titles, authors, tags, and most importantly, of course, the book covers themselves. Now, the book covers have varying sizes, so we need to pre-process them to a uniform 64 by 48 image. We then convert to grayscale and then scale from -1 to 1. We can make our image more high-res and to use all the channels for the image. However, we don't have as much of a hardware as NVIDIA, so one can wish. As our baseline, we turned a basic form of GAN, which is called Deep Convolutional GANs, or DCGANs. To generate images, DCGANs leverage from its cousins from the classification camp, convolutional neural networks. So it uses a lot of convolutions. We have a lot of modifications, however, from not using, for example, max pooling to using hyperbolic tangents for the generator output. Now, as I've said, training GANs are notoriously difficult. So we have these stability tricks, and these are the things that I found very useful. So, for example, we use the ADAM optimizer, which is an adaptive learning rate methodology. It supports gradient descent. Batch normalization is another technique which lessens covariance shift, or the way the parameters change after each gradient step. Training GANs will take a very long time and the generator's output could vary a lot. So batch norm really helps in making things nice and easy. Lastly, we have soft and noisy labels. Soft labels would be converting your 0 label as fake and 1 label or real labels to something softer like 0.3, 0.2, or 0.9 or 1.1. Right? This would help the discriminator to be a little bit less overconfident in its predictions, right? And then we also introduce noisy labels, which is one way again to make the discriminator a bit weaker, right? You just randomly flip some of the labels so you can confuse the discriminator. Since the networks are quite deep, I've divided them into two. So this is how the discriminator looks like. As far as convolutional neural networks go, this is really quite shallow. We don't want the discriminator to be as good as its ResNet cousins, since we want it to be simple so that it would make mistakes. And from those mistakes, the generator could learn something new. Its output is, if you recall, a single number featuring the probability of a real image or a fake image. This is what a generator would look like. It would take an input of 100 dimensional vector, and after successive transposed convolutions, it then outputs this image or 64 by 48 image in grayscale. Now, training GANs is a bit different from other types of neural networks. It's a cycle of back and forth induction and deception. First, the discriminator learns on the real images, right? And this is just for one step. Basically learns how good the discriminator knows the domain. It then gets the current output of the generator and then updates itself on the output of these fake images, right? And then afterwards, the generator will then take the outputs of the discriminator, basically asking the question, is the discriminator fooled enough by our fake images? So it updates itself to fool the discriminator, and the cycle starts anew. In the beginning, the two networks are really dumb, right? The discriminator, however, learns fast that the generator's output is not real at all, right? The generator really just outputs random stuff. However, since it's weaker than its cousins, the CNNs, it will leave some mistakes, and from these mistakes, the generator can learn how to most advantageously update its parameters. Now, to monitor the training process, we can monitor the different kinds of losses in our networks. So for the discriminator, at the beginning it's quite high, but it rapidly decreases, right? It stays low throughout the process. Note that it should never go to zero, zero loss or perfect, since it has nothing left to train or to give the generator. Basically says that everything the generator does is wrong. So that's not something that we do want. The generator, on the other hand, is more stable, right? At the beginning, as you can see here, it can fool the discriminator. However, in the middle, it rises up gradually. So the discriminator becomes more superior. And after the 20,000 iteration, it goes down. But we already ended our process here. So it suggests that we can still train for longer. Now, besides monitoring our losses through line graphs, we can also monitor the generator's outputs, right? So this is what it looks like at the start of training. It looks like a very, unconvincing image of a book, right? And then after 5K, it's still not convincing at all. On 15K, now it's discovering something. Once in a while, it has these ovoid things now and then, right? It has shapes already. In 20K, things are, well, marginally interesting, right? It has eliminated much of the unnecessary details. In this particular image, for example, things are a lot less or a lot more sparse. Really just the important bits, which is the ovoid shape. And after 25,000 iterations, now it's come up with something like this. Now we see some lines here and there, right? And some lines here, right? So this is how we can snapshot or monitor our training process through the images. And for our DCGAN, this is the results, right? So judging from how it looks like, these aren't convincing book covers. It's a bit creepy actually, right? However, the generator outputted the traits of a book cover, right? Its general characteristics. Firstly, something resembling text is present in some of the images, over the top, over the bottom, right? Although it doesn't really resemble anything human, right? It's not language. This is actually a problem for our GANs since we haven't inputted any language model into it. Hence, it will be hard-pressed to rediscover the human language, or English at that. Secondly, it has again those ovoid subjects that I described, right? And sometimes there's a frame structure, right? As you can see, for example, here, there's a frame, right? And also here, there's a frame over the top part of the book, right? And it's suggesting a sort of foreground, background thing happening for our book covers. Now let me talk about another type of GAN, which is semi-supervised GAN, which takes into account the tags in the data, right? So now we also use the tags present in the dataset. It has been reported to generate better results in a shorter amount of time. Trade-off though is it's more complex. There's 3 implementations in the original paper, but our particular implementation will make use of stacking 2 discriminators, right? As before, we will have a generator over here and a discriminator, which outputs if an image is real or not. However, now there's also another network called the supervised discriminator, which outputs also the tag Y, right? And this Y comes from our training data. In our case, it's if the book is fiction, non-fiction, historical, romance, and so on. This methodology can force the discriminator to also learn the tags of the images, right? And it can lead to better clues for the generator. Note that for this particular implementation, our h of x or our hypothesis space or our parameter space is actually shared between our 2 discriminators. So they have the same parameters. But the difference is that the second one also outputs if the image is real or not. In our implementation, we have a subset of the Goodreads book covers dataset, 100 book covers per category, and that kinds of primes our discriminator, right, for better learning. Now, at the cost of adding complexity, our networks can encounter failed states. In one of my runs, sometime after the 39,000 iteration, which is actually outputting already some really nice images, after a bit, some iterations later, it degraded to something like this, right? I don't know for sure why this happened, but it can be actually detected by our generator loss. As you can see here over the right side, this loss suddenly jumped up significantly and stayed there, right? My intuition is that a particularly bad batch led our GAN to a bad plane in our parameter space. Could be that the distribution of the particular distribution of that batch is really bad, right? And it never recovered from there. It's incredibly frustrating if this happens, of course. So my advice is to add monitors to stop training if this happens, right? So in this case, it already stopped up after the 4,000 iteration, saving me some power. And backtracking, right? So what if after we've encountered this bad state, then let's go back to the best state that it has found so far and repeat training from there. Now for a successful training process, we have these snapshots. And what I'm really glad about here is that it seems to have been training faster. So for example, at the start of training, we see these random images. And then after the 2000 iteration, it already sees the frames and some inkling of text, right? These, shall we say, vertical lines. And over the 6000 iteration, now it has some foreground qualities as well. This looks kind of like a heart to me. And this looks like a sky. For some reason, this looks like a tree. Maybe I'm hallucinating or something. And after the 8000 iteration, now we see something like this, right? We have these blocky things over the some part of the images, right? And we have these, we have that. So we have block text over the top side and a block text over the bottom side. So that's very interesting. And only after 8000 iterations. For the training process, we've averaged the discriminator loss, just so to summarize things. In the beginning, there is this period of very high loss over here for the discriminator, right? And low loss for the generator, right? So this is the case where the generator is repeatedly fooling the discriminator. The discriminator, however, rapidly corrected itself and stays superior in the training, right? As you can see here, the generator loss is slightly increasing, but it's, stable at that point. As before though, the best training process is that at some point the discriminator loss goes up, therefore it is being fooled by the generator since it outputs a progressively better quality image at some point in time. This is how the semi-supervised GAN results look like after less iterations actually than our DCGAN. As you can see, it has forgone some of the ovoid things. It's very close to what we're trying to find. Now, comparing both outputs side by side, we see that the SGAN has reached quite the same level of the SGAN output in a shorter amount of time, right? For example, it has discovered, the concept of borders around the text, right? Also here, you need to have a rectangle border around the text. The SGAN also has abandoned these ovoid shapes as the foreground of the images, right? And it's not outputting those circles anymore. So this looks like a half of a mushroom cloud or something. This kind of looks like a chair. This is very reminiscent of a penguin book, right? You see those books that has a black frame at the bottom, right? So both though have not yet learned the concept of human language. These are just lines, right? So it's as expected, we don't have a language model inputted into the system. Now, a third type of GAN is called conditional GANs, and it's my ongoing work. Now, given a category, we output the most likely image. So as before, we have the generator and we have discriminator, and the difference now is that the discriminator also takes into account or takes as input the input label of the image. So it can do something like if you want it to output a smiling face, it can output a smiling face. If you want to have a sad face, it can output a sad face. If you want a fiction book, it can conceivably create a fiction book, or of a non-fiction book, it gives a non-fiction book, right? And that's how SGANs work. And it's very interesting since you can control the output of the generator. So to end, this really is my money slide. Uh, this is how DCGANs and SGANs work. And as you can see here, these books don't really capture or don't really resemble things like real book covers, but it outputs the characteristics of these book covers. So again, until the next vlog, thank you.